Welcome. For all of you who don't know me anymore, I'm Jessica Liu. I used to be faculty here at IFA. Matt was one of my first graduate students here along with Kelly Lockhart, and I'm happy to be back for Matt's defense on this very special day. And maybe if we could hit the lights here, if I remember.
I think it's the switches on top, yeah.
Well,
We're going to turn this one on the side.
That'll do.
Turn the flippers up.
These up.
Yeah.
Oh, yeah, there we go. All right, that's much better. Thank you. Okay, so I just wanted to kick us off today with the very traditional tribute to the student in question. Soon not to be anymore. Hi, Rolf. Make sure to mute now that you're on sound. Okay, so let's get started. First, when Matt first started grad school, he came to Hawaii, fresh off the boat or the plane, as it may be, a literal Boy Scout. Full of enthusiasm, he joined his colleagues, his classmates, way back in 2012, and showed more enthusiasm than just about anybody could stand. That was his normal mode of operation. Everyone who's on remote may want to mute. So he started grad school with his favorite map in mind. A typical grad student map is something like this. You get cryptic clues in the beginning, lots of codes. It's not really a straight path by any stretch of the imagination. Ultimately, his goal was to acquire his PhD, and that's what's brought us here today. Now, from Matt's perspective, I've traveled with him a few times, and given his very famous sense of direction, I was a little worried that he saw the map more like this. If you've ever traveled with Matt, you'll know what I'm talking about. Here's a hike here. I think Nicholas McConnell is afraid that Matt's leading the hike, and that's a problem.
Yeah, hell yeah.
But along the way, he encountered exotic foods, worldly adventures, traveling everywhere. New challenges, especially with riding and maintaining a moped. Yeah, for sure. Strange alien blobs. I have no idea what that thing was. Acquired some new skills. My real question is, did you actually ever surf on water?
Twice.
Twice.
Twice. Yeah. So a little bit.
And occasionally he needed inspiration and cheer from friends, including inspiring memes from the internet, as all grad students these days do. And endless questions from future seekers of astro wisdom. If you don't know Matt, he is a giver of knowledge to the world, and we're all very thankful for that, including both in Hawaii and at Berkeley now as well. And of course, lots of fun distractions. Matt certainly knows how to have a good time. And never once through his entire graduate school journey did he ever lose his cheer that I ever saw. He certainly brought a light to my research group, and I'm very thankful for everything he's given. He's been a tremendous graduate student. And for those of you who don't know, Matt had a bevy of postdoc offers. He'll be heading to UCLA to work in the Galactic Center group this fall, and proceeding on his postdoc journey in astronomy with this map to guide him. And a good Hawaii speed limit, too. So let's give Matt a big round of applause for making it this far, and hope to hear from him.
Yeah, I guess I have to choose here. And here. Okay, wonderful. Well, Jessica, thank you so much for that introduction, and thanks to everyone for being here today and all the folks calling in online. So today I'll be talking about the work I've done for my dissertation, looking at young massive clusters close to the galactic center, in particular, their initial mass function. So the initial mass function, this is a property of star formation, so I thought I'd start off just with a quick introduction on how we think the majority of stars in the universe have formed. Right? And the basic idea is that you start off with a giant cloud of molecular dust and gas floating out there in space, and then for one reason or another, that cloud begins to collapse under the force of gravity. As it collapses, the cloud begins to fragment into smaller and smaller clumps of materials until you form stars with a whole range of stellar masses. Eventually, at the end of the day, you have a nice star cluster. right? So the initial mass function, or IMF, is the distribution of stars in this star cluster. Or more formally, it's the distribution of stars formed during the star formation process. Now, an interesting fact about the initial mass function, or the IMF, is when we study it in nearby star-forming regions and star clusters in the Milky Way, and also star clusters in nearby galaxies, like the LMC and SMC, it looks pretty much the same wherever we look. This is just showing this local initial mass function. We have frequency versus stellar mass here. And the high mass stars are well described by a single power law that increases up until you get to around half a solar mass or so, and then the mass function turns over. Now, because we see this IMF everywhere, this led to the thought that this is a universal property of star formation, and so this IMF is applied to studies of stellar populations all around the universe, right? But so this is all well and good, as long as the stellar population that you're studying with this IMF was born in a similar environment to local star-forming regions. It's still an open question whether or not this IMF is applicable to more extreme star formation environments. For example, we can look at the galactic center. So this is just a mid-infrared image of the galactic center. This is about 1 kiloparsec. It's kind of the size of the image here. And I've marked out the position of the central supermassive black hole by this white arrow here. Now, when you look at the galactic center, you look at the molecular clouds, and you find that the temperatures, densities, and turbulent properties of these clouds are about 5 to 10 times higher than what we observe for local star-forming regions. Right? So you take that in addition to the strong tidal field environment, the increased magnetic fields, and we have an extreme star formation environment practically in our backyard. Right? So it gives us an opportunity to explore what the IMF will behave in such an how the IMF will behave in these environments. So this is where my thesis comes in. In particular, I'm studying the arches and quintuplet clusters, which are 2 young massive clusters with a projected distance of just 30 parsecs or so from the central supermassive black hole. Now, their physical distance, we don't know exactly where they're located, but we know they're within the inner 200 parsecs of the galaxy or so. So they're embedded in this galactic center environment. Now, these objects are wonderful for studying the IMF because they're incredibly young. They're both less than 5 million years old, and so stellar evolution hasn't had a lot of time to really significantly affect their mass function. Also, because they're so massive, they're about 10 to the 4 solar masses, we have a large stellar population to work with. Right? So for my thesis, the goal is to study the IMF of these arches and quintuplet clusters in order to gain insight to how the IMF behaves in this extreme star formation environment. Okay, so although the arches and quintuplet are wonderful objects to study, unfortunately, it's actually very difficult to make this observation. And a big reason for this is that there's a significant amount of extinction along the line of sight between us and to the clusters. Right? So what that means is that there's a bunch of gas and dust and other material in the way that extinguishes the starlight from the cluster. And worse than this, the amount of extinction you see changes as a function of position in the field. And you can see that from this Hubble Space Telescope image of the Arches cluster. You can see that the density of background field stars appears to change, right? Low density here, high density over here. Well, that's not due to any intrinsic property of the Milky Way or whatever. This is due to the fact that you have different amounts of extinctions across the field. It's something we call differential extinction. And a consequence of this differential extinction is that it's very hard to figure out what stars in this very crowded field truly belong to the cluster and which stars are just part of the background population. So the way we're going to get around this is by using astrometry, which is the precise measurement of stellar positions. And if you can obtain astrometry over a series of over a certain time baseline, we can measure the proper motions of the stars. Right? This is the true motions of the stars on the sky. And we can take advantage of the fact that stars that are part of the cluster move across the sky with a common proper motion. Right? That's because these stars are gravitationally bound. Whereas the field population has a much more randomized distribution of proper motions. Right? So with proper motions, it gives us a way to identify cluster members that's really not affected by the differential extinction. So to make these measurements, we have Hubble Space Telescope, or HST, observations of both clusters in the WIFC-3IR filter camera. The filters are the F127M and F153M filters. That's roughly J and H band. And we have 4 epochs of observations over 6 years. Right? And with this data set, we get a total field of view of 120 by 120 arc seconds, which is shown by the red box here. And this field of view is significantly larger than previous proper motion-based studies of these clusters. In the case of the ARCHES cluster, our field of view is 100 times larger than previous studies, which have proper motion-based studies, which have focused on the cluster core region. So we have a large field of view, we can get a large cluster sample, and then a cleaner cluster sample than past literature studies. This is how we'll measure the IMF. Okay, so from now, I'm going to focus mainly on the ARCHES cluster, and I'll come to the Quintuplet cluster kind of at the end here. But okay, so how do we measure the IMF of the ARCHES cluster? Well, the first thing we need to do, right, is we need to identify cluster members. Sorry, this slide takes a little while to, there we go. So as I said before, right, we are identifying cluster members using our proper motions, and we were successful in extracting high precision proper motions from our observations. This plot here, this is proper motion error as a function of magnitude in the field, and we achieve precisions as good as 0.04, 0.05 milliarc seconds per year for the brightest stars in the field, right? And so if you take this sample and you adopt an error cut to get rid of the high error stars, and you're just left with everything else. If you plot these stars in what's called the vector point diagram, which is just a plot of proper motion in the y direction versus proper motion in the x, what you find is you get a nice clump of stars, right, that belongs to the cluster, right? These are all the cluster stars that are moving across the sky with this common proper motion. Whereas the field stars, right, are spread out in much wider distribution. So what we did is we modeled the kinematic distribution of the cluster and field using a Gaussian mixture model. And then once we have this model, we can calculate individual cluster membership probabilities for each star based on their proper motion. And with these membership probabilities, they allow us to go from a rather complicated color magnitude diagram, something that looks like this, to isolating all stars with, say, membership probabilities greater than 0.3, which I've highlighted by these red points here. You take this one step further, you take this sample and apply a correction for the differential extinction, and we begin to see a cluster sequence emerge. Now, an important part of our analysis is we need to be able to characterize our observational completeness, right? How well can we truly observe these stars, both as a function of magnitude, a function of brightness, and also as a function of position in the field. And to do this, we do artificial star plant and recovery tests, and we find that we obtain at least 30% completeness all the way down to 21st magnitude at F153M. This corresponds to about 1.8 solar masses, and this is going to be the lower mass limit to our sample. Right? So at the end of the day, we end up with a cluster sample of 980 stars with membership probabilities greater than 0.3. But we don't treat each star as just one. We weight each star by that membership probability. So in reality, when you sum the membership probabilities together, we end up with 638 members. Now, I should note that in the case of the ARCHES cluster, these members are distributed in a radius range of 0.25 parsecs to 3 parsecs. We aren't able to get into the cluster core region simply because the stellar density is so high. Even with HST, our observational completeness is too low. So we omit the cluster core in this analysis. Okay, so we have our cluster membership probabilities. The next thing we need to do is we need to measure the cluster structure, right? We need to have an understanding of how big the cluster truly is, so how much of it is in our observations. And also, we need to be able to characterize mass segregation, which is a process by which the high mass stars in the clusters preferentially concentrate toward the center. So this was actually my 699 project with Jessica, which was a good project. But anyway, before we started this work for the ARCHES cluster, the radial profile of the cluster, which is just stellar density as a function of radius, had only been measured for the inner 0.4 parsecs or so. And it was predicted that the cluster would have a tidal radius that at most would be 2.5 parsecs, And so what that means is that the cluster size, the total profile would look at the biggest, something looking like this black dashed line here. Well, when we use our proper motion selected sample, we found that this wasn't the case. We found that the radial profile of the cluster in the at high radii was well described just by a single power law, and we ruled out any sort of tidal truncation to 3 sigma all the way out to 2.8 parsecs. Right? So this tells us that the ARCHES cluster is actually significantly larger than what was previously anticipated. Now, going one step further, we can take our cluster sample, right, and split it up into our bright high mass stars and faint low mass stars, and take a look at their radial profiles individually. That's what I'm showing here on this plot. Again, it's stellar density. It's a function of radius. And the black profile here, well, that's the profile of your bright high mass stars, whereas the red profile is the faint low mass stars. Right? So we see that the bright star profile is steeper, right? And well, this is telling us that we have mass segregation. These high mass stars are more centrally concentrated. They have a steeper profile than the low mass stars. Now, this was not a new result. Several authors had pointed out that the ARCHES is mass segregated, but we were the first to measure this mass segregation out to such large radii, and we parameterized it in terms of these magnitude-dependent radial profiles, which end up being a big part of our IMF analysis down the road. Okay, great. So then, the next step we have to do is we have to make sure that we can properly correct for this pesky extinction. Now, in order to correct for extinction, one of the things we have to understand is the extinction law, which is just a function that describes how the extinction changes as a function of wavelength. My original thesis plan was that we could just take an extinction law from the literature and plug it into our data analysis and go. Unfortunately, as we started looking at our ARCHES data, we realized that this wasn't going to work. We found that actually, on top of the ARCHES data, it was also, we had HST observations of Westerlin 1, which is another young massive cluster, not quite at the galactic center, but still in the inner regions of the galaxy. And what we found was, in the case of Westerlin 1, we could use proper motions to identify main sequence cluster members. And when you plotted those main sequence members in a color-color diagram, well, the observed sequence didn't match any of the predictions using the extinction laws in the literature. Right? In the case of the ARCHES cluster, we only have 2 filters for photometry, so we can't use a color diagram. But what we can do is we can calculate the distances of red clump stars in our field. Now, red clump stars, these are evolved helium-burning giants. So they're older stars that are not part of the ARCHES cluster itself. They're part of the bulge population. And it's been shown that red clump stars, their distribution is sharply peaked at the galactic center, which, well, that distance I'm showing by this red dashed line here. So what we found is that using extinction laws from the literature, the distribution of distances for red clump stars, right, is systematically too close to us by about 1.5 kiloparsecs, right? So this really indicated that there was a problem with the extinction law. So this sparked a whole new project, a whole new effort to measure the extinction law to the ARCHES cluster, which is what we did. We were able to actually combine the ARCHES and Westerlin 1 data sets to measure the extinction law between 0.8 and 2.2 microns using a new methodology that doesn't make any sort of assumption regarding what the functional form of this extinction law is. And here I'm showing our result. This is a plot of extinction, right, as a function of wavelength. So this is our extinction law. And the value of the law we find is shown by this red curve here. With the uncertainties, they're kind of hard to see. The uncertainties are shown by the red shaded region. In fact, our uncertainties are about 5%. Now, what you notice immediately is that our extinction law is significantly steeper than the standard extinction law used for the Milky Way, ISM. That's by this black curve here, the Cardelli et al. 1989 law. And it's also steeper than the extinction law often used for the galactic center from Nishiyama et al. 2009. That's shown here by this green curve. Now, another important and kind of subtle result that come out of this is that we found that the extinction law is inconsistent with a single power law over this mass range. And this is significant because folks often assume that in this wavelength regime, you have a power law. Well, when you have HST precision photometry, you can show that there are subtle structures in this extinction law, and it's not just a simple power law. So this is a large topic. Could give a whole talk on this, but we'll move on. Okay, great. So now we have everything in place. Now we can go ahead and measure the extinction law for the ARCHES cluster. And the way we're going to do this is with a forward modeling approach. What that means is that we are going to generate an artificial cluster using stellar models, some given parameters, and then simulate observations of that cluster. And then we compare the synthetic observations to the actual observations, right, in order to find the best match. Once we have the best match, well, then we know the properties of the ARCHES cluster. Now, using this forward modeling approach, we're able to simultaneously fit the IMF of the cluster along with other cluster properties while accounting for things like observational errors, or completeness, mass segregation, and stellar multiplicity. So this is really a powerful approach. Now, I should mention that in the case of the ARCHES cluster, we have an additional data set on top of our HST observations. We have additional Keck OSIRIS spectroscopy in the K-band of a sample of 5 cluster members close to the inner core region here. Right, so the goal with these observations are to measure the effective temperatures of these stars, right, and that will allow us to help calibrate the mass-luminosity relationship in our forward modeling. And I'll get back to that a little bit. Okay, so how do we build our model? Well, we're going to, for the IMF, we're going to assume a single power law model. So dN/dm goes as m to the minus alpha, where for the local IMF, the IMF slope is alpha of 2.3. Now, when we compare, right, our synthetic observations to the real data, we're going to do this comparison in 4 separate ways. And so that gives us 4 components of our likelihood equation. Right? The first way, the first component of this comparison is that we're going to look at the distribution of stars in color magnitude space. Right? We're going to look at the star brightnesses and the colors between the synthetic observations and then our real observations. Right? Second component we're going to look at the total number of observed stars. We'll also look at the number of Wolf-Rayet stars. Wolf-Rayet stars are high mass, highly evolved stars near the end of their lives, and the number of which actually serves as a nice age indicator for the cluster. And then finally, this 4th component, we have the spectroscopic component. Right? We've measured the effective temperature of a handful of stars at a certain observed magnitude, and we can compare that to what our synthetic models predict. Okay, so here we go into our results. So here I'm showing the posterior probability distribution for this high mass IMF slope alpha. Right? The probability distribution is shown by the red histogram. Now what we find is we get a value of alpha of 1.76 plus or minus 0.03 as a statistical error, with an additional 0.05 as a systematic error. And now what you can see from this plot is that this value is significantly lower than what we measure for the local IMF, which is shown by this black dashed line here, with the uncertainty shown by the black shaded region. In fact, our value is 9 sigma shallower than the local value if you ignore the uncertainty in that local value, which is often done. If you consider that uncertainty, the difference is about at 1.8 sigma. Now, this result is also 8 sigma shallower than what's been measured for young clusters in the Andromeda galaxy, M31. So you can see we have a little better measurement here, much smaller error bars. When you compare to this measurement, right, we're 8 sigma shallower. Right? So what is this saying? This is saying that the ARCHES cluster IMF is top heavy, meaning the mass function slope is shallower than what you'd expect, and so you have an overabundance of high mass stars. We also have constraints for other cluster parameters, but I'm not going to dive into those today. Okay, so here I'm just showing a comparison between our best fit synthetic model and our data. So the top panel, this is color magnitude diagram looking at the density of stars, right? So a Hess diagram, if you're familiar with the term. But in the left here is our observed cluster here. In the middle, we have our best fit model. And then third panel, we have the residuals between the two. Now, in this plot over here, I'm showing the 1D luminosity function, right? So just number of stars as a function of magnitude. And you can see the comparison between the observations, which are the black points, and the best fit model, which is the red line with the uncertainties in the red shaded region. And then here, in this final panel, I'm showing the HR diagram for these spectroscopic stars. This is a plot of luminosity as a function of temperature, and again, you can see that our stars are the black points. The model is shown by the red line, right? So our model gives a pretty good fit to the data. Now, up to this point, I haven't yet shown a mass function, right? Number of stars as a function of mass, and that's because assigning a mass to an individual star in our field is actually a bit of a tricky business. So what we've done here is we've used our best fit cluster model in order to assign masses to the observed stars. Specifically, what we're doing is we're looking in this color magnitude diagram. We are taking our synthetic cluster, and at a given point in the color magnitude diagram, we're looking at the distribution of stellar masses, again, in the synthetic cluster. And then when we go to our real observations, for a data point at that same point in color magnitude space, we assign it a probability distribution for the stellar mass equal to the stellar mass distribution of our synthetic model. So basically, the upshot of all this is that the mass functions I'm going to show here, these are model-dependent mass functions, right? They depend on our best fit. We don't use them at all in our fit. This is something we calculate afterwards. It really kind of serves as a sanity check. But anyway, so describing what's going on in this plot, the red solid points is our observed model-dependent mass function, all right, and compared to the mass function predicted by our best fit model, which again is this red solid line with the 1 sigma uncertainties shown by the red shaded regions. You see, we have a pretty good match. We can, looking at this another way, right, we can take our best fit cluster model, and instead of using the top-heavy IMF, we can go ahead and adopt the local IMF value, which gives you a steeper mass function, right? So the model would look something like this blue dashed line here. However, if you calculate a mass function using this model, right, we see that you get systematically too many high mass stars than one would expect with this mass function. So this is just reiterating that we cannot, the ARCH's mass function, the ARCH's observations cannot be described by the local IMF. Oh, sorry, I also should mention, I have one more set of data points out here. This corresponds to the total number of Wolf-Rayet stars. The observations are shown by the black star here, the uncertainties, and well, that value predicted by our best fit model is the red square, and then the blue square corresponds to the local IMF. Okay, so taking a step back, what does this all mean? Well, it turns out that the IMF slope that we measure is actually similar to the IMF slope that's been measured for the young nuclear cluster, which is a young massive cluster in the galactic center, in fact, constrained to within the central parsec of the central supermassive black hole, right? So to show that, this is a plot of IMF slope alpha as a function of mass. You can see our ARCH's measurement is by this red star, and this young nuclear cluster measurement is this red point here. And the values are similar to each other, and they're significantly shallower than the local IMF, which is shown by the black dash line, and also the measurement of young clusters in M31, which I show by the cyan box. Right? So you could ask at this point, okay, we see signs of a variation here, but is this variation truly due to the galactic center environment, or is this just a property of young massive clusters? Well, fortunately, there is a sample of young massive clusters in the Milky Way disk, right? So outside the galactic center environment that we can use as a comparison sample to, our cluster point here. And so I'm showing the mass functions of these clusters as the blue points here. And you can see the values you get are consistent with the local IMF, right? So this is suggesting that the IMF that we're seeing, this variation, is indeed due to the galactic center environment. Well, it's not quite that clean yet, because there are two young massive clusters in the Milky Way disk, Westland 1, which I'm shown by the purple points here, and then NGC 3603, which are these turquoise triangles. Oh, I guess it doesn't come up well on the projector, but anyway, points are right here. Anyway, there are these two young massive clusters in the disk that might also be showing a top-heavy IMF, similar to the arches and similar to the young nuclear cluster. But still, it's a little tricky to interpret because you might notice right away I have 2 data points here for the high mass range of the IMF, both corresponding to Westerlo 1. 2 measurements from the literature. One is consistent with the local IMF, the other is this top-heavy value. Right? So this is kind of an unresolved problem in the literature as of now. And in the case of NGC 3603, well, 1 point has very large error bars, so kind of tough to say anything there. And the second data point, in that study, the authors were limited to studying the IMF in just the central half of the cluster. And they note that their measurement can be biased by mass segregation, which we know exists, right? You focus on the center of the cluster, you have an artificial overabundance of high mass stars, you might get an artificially top-heavy IMF you don't account for. So all in all, I think the proper statement at this point to make is that we are starting to see tentative evidence that the galactic center environment is inducing a top-heavy IMF, but we require more observations, more work, especially for these clusters in the Milky Way disk, in order to, really make this a firm conclusion. So this has been, a pretty nice full story as of now. But there's one more complication we have to look at, and that's instead of modeling the IMF using a single power law, what happens if we use a 2-segment power law model, right? So we have the NDM, right, goes as m to the minus alpha, same as before. But now for the high mass stars, you have, a certain alpha 1 down to some break mass, MB, and then below the break mass, you have a second power law, and with a different value. Now, for the local IMF, this break mass occurs at half a solar mass, right? So we wouldn't expect to see this in our data, right? Because remember, our data only goes down to 1.8 solar masses. Well, to our surprise, when we ran the analysis, we found actually a nicely constrained model with the 2-segment IMF that did fit our data. And so I'm showing here, this is posterior probability distributions for several parameters of the IMF. But I want to draw your attention to the central panel here, which is the posterior distribution for this break mass MB. Again, it's the red histogram is our result. And we get a value of 5.11, okay, plus 1.3 minus 0.65 solar masses, right? So this is an order of magnitude larger than the IMF we observe locally, which I'm showing by the black dashed line here, and also what we observe in the Orion Nebula, shown here by the blue line, blue shaded region. Further, if we look at the high mass IMF slope, right, in this model, so looking at the same mass function slope we were looking at before, we get a value of 2.1 plus or minus 0.1, a value that is much more consistent with the local IMF and also the value measured for these clusters in M31, right? So in a sense, what we're seeing here is that if you have a 2-segment IMF model, rather than having an overabundance of high mass stars, we have more a deficit of low mass stars, right? So kind of use a phrase, it's bottom light instead of top heavy. And that's because this break mass is significantly higher, right, than what you observe for the local IMF. Okay, and comparing to data, I'm not showing the full set of plots here, but just showing here's the 1D luminosity function again. Again, the black points are the observations. The red line is this 2-segment IMF model. And then I'm showing this model-dependent mass function here. So we have these 2 models. How can we decide which one better fits the data? Well, all of our analysis is done in a Bayesian inference framework, and so there are some statistical tools we can use to get at this question. In particular, we have the Bayesian information criterion, or BIP. And I'm not going to go into the details of that, but the result is that we're in a position where the 2-segment IMF model is not statistically favored, but at the same time, we cannot rule it out. So unfortunately, we're kind of in this position that you could go either with the 1-segment IMF model or the 2-segment IMF model. Now, I should emphasize that regardless of which way you go, the Arches cluster IMF is significantly different than the local IMF. So that's really the big point. Okay, so if we have these IMF variations toward the in the Arches cluster, and if it's due to the galactic center environment, this has some interesting implications for our understanding of star formation. right? And to discuss this, I'll bring us back to this IMF plot of the local IMF, right? Frequency is a function of mass. Only now I've labeled this high mass IMF slope alpha, and then I've kind of shaded the break mass region, MB. Well, there have been a series of studies, theoretical studies of star formation, kind of putting all the physics in there, that have suggested that if you go to extreme star formation environments, like the galactic center, where you have higher gas temperatures, you might expect this break mass to increase. Right? You'd expect the break mass to increase, but it really wouldn't affect that high mass IMF slope alpha. Right? And physically what's going on, right, those higher gas temperatures lead to a higher thermal Jeans mass. Basically it just means you need more mass in order to induce gravitational collapse. Now, this is actually rather similar to our two-segment IMF solution. Right? So this is potentially a viable explanation of what's going on. There's been another set of theoretical models that in fact have been popular quite recently, trying to understand the origin of this high mass IMF slope alpha, right? And these studies predict that the slope of this, this slope is set by the turbulent properties of the molecular cloud. So you go to the galactic center, you have significantly higher turbulence, you would expect increased fragmentation, and so this would favor the formation of low mass stars. This would steepen, right, this mass function. This would make alpha increase, steeper. This is not consistent with our results. In the one-segment IMF case, we observed the opposite. We observed this mass function getting more shallow. And in the two-segment IMF case, we're not seeing really a significant variation at all. Right now, there's been a lot of work recently simulating star formation, kind of including all the kind of physics, including magnetic fields and stellar radiated feedback and really polar jets. And so there's a lot more work needed to be done on the theoretical side to understand all the physical processes just that create the IMF. Okay, so I've talked a lot about the Arches cluster. You may be asking, well, what about the quintuplet? The quintuplet is another young massive cluster near the galactic center. It'll give us another data point to look at. And it's slightly older than the Arches cluster, by about 1 or 2 million years. Might be kind of interesting to look at the differences. And the data set we have on the quintuplet is practically identical to what we have for the Arches. Right? So everything that we've developed for the Arches, we can apply to the quintuplet. Well, this is what we've begun to do. For the last year, I've been working with a Berkeley undergrad student, Nicholas Rui, on a study of the structure of the quintuplet cluster. And he's done a fantastic job. This work is nearly complete and should be submitted real soon. And his big result is that if you look at the radial density profile for the quintuplet cluster, shown here in red, it's about twice as large than what you see for the Arches cluster, which is shown by the blue lines here and then also the magenta lines. Right, so this, what we may be looking at is we may be looking at the consequence of the evolution of star clusters in the extreme tidal field near the galactic center. Right, the quintuplet is older, it's been exposed to this tidal field longer, right, it's getting puffed out. Similar to the Arches, we find no evidence for a tidal radius in the quintuplet cluster out to 3 parsecs. It's outer profile well described by a single power law. And also we see the signatures of mass segregation that we characterize using magnitude-dependent gradient profiles. So this has been great. Now everything's ready to plug the quintuplet data into our IMF analysis. And this is something I'm going to be actively working on this summer. Okay, and so with that, I kind of come to our conclusions, right? So we've been working on a proper motion-based study of the IMF of the Arches cluster, mostly so far. And these proper motions give us a significantly cleaner cluster sample than what previous studies have had. And with this clean cluster sample, we have measured the radial profile out to 3 parsecs for the first time. We've also used the HST photometry to precisely measure the extinction law, right, in the wavelength range that we're working with. And putting this all together, we find that the Arches cluster IMF is inconsistent with the standard Milky Way IMF. How it's inconsistent depends on which IMF model you assume, right? If you assume a one-segment IMF, we have a top-heavy result where the high mass slope alpha is significantly lower than the standard value. And if you do a two-segment IMF, the result you get is, well, bottom left, in that the break mass, the turnover mass of the mass function, is significantly higher than the standard IMF. Comparing these measurements with past young massive clusters in the Milky Way, we find tentative evidence that the IMF variations are due to the galactic center environment, though we'll need more studies of young massive disks in the Milky Way disk, and also having the quintuplet cluster as another data point will be great to solidify that point. So indeed, stay tuned for this IMF analysis of the quintuplet cluster. So before I take questions, I just have a few quick acknowledgements. I want to have a shout out here. I've been privileged to work with a wonderful group of people. First off, I'd like to thank, of course, my advisor, Jessica. She's been a wonderful mentor and role model for me, and has always managed to find me whenever I get lost at conferences, which, as she suggested, this happens a lot, so I really can't thank her enough. Of course, I have my thesis committee, Rolf, Mike, Mark, Bo, and Prasad. These folks have really helped guide this project from the beginning, and Rolf additionally was my first 699 advisor, so got me started at grad level research. I've been honored to work with a great group of collaborators that have been very insightful and really contributed a lot to this work. And also, the research group over at Jessica Liu's research group over at Berkeley, they've been a great group to bounce ideas off of, and I've really learned a lot from those folks as well. I'd like to thank also the IFA and Berkeley staff who have helped me navigate the logistical challenges of being a visiting student at Berkeley, but actually enrolled here. And I'd really like to thank the IFA grad student community and also the grad student community at Berkeley, which have made me feel welcome really from day one. And it's been, a wonderful 6 years. Special shout out to my cohort, right? We have Lori, BJ, Mike, Hassan, Evan, and Sean. And also a special shout out to Kimberly Aller, who's been very incredibly supportive of me and patient with me. Even though I may have scheduled this defense on her birthday. Yeah, so thanks to her. And finally, just to wrap up, I would not be here without the love and support of my family. My parents, my siblings who have supported me from day one. And also my grandma, who to this day, she still sends me newspaper clippings of astronomy articles. So with that, I'll end, and I can take questions. So, thank you.
All right, so first up, we'll have questions from everybody but the committee. And then after we finish with questions, then we will split. The committee will remain and ask a few questions of Matt then in a private session, and then hopefully very shortly after that, we'll have some celebrations. So first off, let's have any questions from in the room from non-committee members.
Andrew.
Question about the extinction law that's not fit by the single power law. Can you use that to say anything to characterize the properties of the dust between here and the galactic center?
Yeah, so that's a great question. In principle, we can. Okay, I won't head all the way back, but yeah, so that extinction law, right, the shape of the extinction law is a function of the grain properties between us and the galactic center. What's interesting is that a lot of theoretical studies looking at the structure of the extinction law, they kind of ignore the near-infrared region because they say, oh, it's a single power law. So there actually has not been a lot of detailed theoretical studies of what these slight substructures may physically mean. So that would be an area of more work. Hopefully with the age of, especially when JWST gets online, we have, space-based near-infrared photometry out the wazoo, we're really going to need to be able to characterize that extinction law and really understand what's causing it. Roy.
So following up on extinction, you didn't mention whether you did attempted to rederive the extinction law for the quintuplet cluster and whether it matches what you get in arches. It looks like the differential extinction is a lot less for the quintuplet.
Yeah, so that's true. The differential extinction is less for the quintuplet cluster. We haven't formally done that. Oh gosh, maybe this was not a good idea. We haven't rederived the extinction law for the quintuplet cluster, but the thought is that the clusters are so close together that they share the same line of sight, that their extinction laws should be similar. But this is something that, we have all the machinery, we have the observations, right? This is something we could explore. But for now, we're assuming that the extinction law for the quintuplet is the same as what we see for the arches. Sam?
So you mentioned that you're getting spectroscopic temperatures for some of these stars. How are you estimating those temperatures?
Yeah. So for the spectroscopy, we are comparing the K-band spectra to non-LTE CMF-Gen stellar models. These are incredibly hot stars, so we need to take non-local thermodynamic equilibrium effects into account. And it's not. So basically, we're comparing the synthetic spectra with the observed spectra. Just trying to get the best fit. And estimating the uncertainties, right? How far can we tweak the temperature until the models no longer fit the data?
So I don't know if this would be possible for those stars, but maybe you could, if there's a way to measure the continuum as well, you could use that to compare against your spectroscopic derived temperatures.
Yeah, so that would be awesome. The Keck OSIRIS instrument, I don't think we have it flux calibrated. So I don't think we can extract out the continuum. I'd have to think about that, but we specifically normalized out the continuum so we didn't have to worry about that flux calibration. But, yeah, I'd have to think about that. Oh, yeah, okay. We're also, far in the infrared, right? So we don't have a peak from the infrared, we're on the LED scale. So, yes, thank you. Yeah.
So at high redshifts, there's these really dusty, luminous galaxies, and it's long been thought that they have top-heavy IMFs. And just yesterday, there was a Nature paper that seemed to be observationally confirming that. I wondered if that kind of environment could, or just any kind of comparisons you could make between that kind of environment and what you're studying here, whether that would provide some insights on what's causing it.
Yeah, that's definitely true. The Galactic Center has been pointed to as an analog for these high redshift. So it's usually we're trying to use, because what's nice about the Galactic Center, right, is that when we're measuring the IMF, we can do it in a resolved manner, right? We're counting individual stars, whereas when we're working with the high redshift galaxies, we're trying to model the the combined stellar spectra. It's a little bit tricky. But yeah, there's definitely a strong synergy between kind of these high redshift galaxies and what's observed locally. I haven't seen that recent paper, but I know there's been a lot of talk of bottom-heavy IMFs in the centers of elliptical galaxies, which are thought to have been similar starburst environments. But it's really a big open question right now. So our hope is that our study of the IMF of the Galactic Center can give us more insight to the high redshift IMF.
Are there any more clusters that you can do this on, or beyond the two? Because right now you have statements saying, the Galactic Center environment and the local IMF. Is there any way you can bring that into more dimensions and sort of understand it in a more granular?
Yeah. Unfortunately, we only know of the 3 young massive clusters in the Galactic Center. So the young nuclear cluster, the arches, and the quintuplet. If you start, obviously you have large populations of stars in general in the Galactic Center, but it gets tricky because as soon as you move out of star clusters, they're not at the same age. There's a lot more uncertainties in the models because of the age uncertainty, and they're older stars, so the high mass stars have evolved. So unfortunately, as of now, we don't really know of a lot of other populations at the Galactic Center we could use to do this. But certainly as as our observational facilities get better, hopefully we can observe more clusters, not just at the Galactic Center, but in just a wider range of environments in the Milky Way, just in general. Look at this, but yeah. Well,
the shift to a high break mass, high solar masses is really interesting. Has that been seen or hinted at anywhere else?
It actually has been hinted at for the arches in the past, but it was interesting in that it was hinted that there might be a higher break mass in the arches, but then there was a slew of papers saying no, there isn't a higher break mass. So I'm trying to think outside of the arches. I do not know offhand of any. I don't know of any offhand any break mass as high as 5 solar masses. So I don't know offhand. I'd have to look through the literature a little bit more.
All right, do we have any questions from remote land non-committee members? Go ahead and speak because we can't see your raised hands. So,
Oh, and we have to make sure the sound is up, but I think the sound's up.
yeah.
Okay.
Okay. I want to say thanks again to Matt for an outstanding job, and let's give him a round of applause before we